Welcome to our DSA Part 2 assignment. Today, our team will be exploring two fundamental sorting algorithms in computer science, merge sort and heap sort. Looking at merge sort first, this algorithm embodies the classic divide and conquer approach. It recursively divides an array until we reach individual elements, then merges these sorted subarrays back together. With a time complexity of O bracket n log n across all scenarios and requiring O bracket n auxiliary space, merge sort guarantees predictable performance regardless of the input data. What makes merge sort particularly valuable is its stability. It preserves the relative order of equal elements. This makes it ideal for applications involving linked lists and external sorting operations where data may not fit entirely in memory. Additionally, its divide and conquer nature lends itself exceptionally well to parallel processing implementations, which is why we see it widely adopted in database systems where reliability and predictability are paramount. In contrast, heap sort takes a different approach by leveraging the binary heap data structure. This algorithm works in two phases. First, building a max heap from the input array, then repeatedly extracting the maximum element to sort the data. Like merge sort, it maintains an O bracket n log n time complexity, but with a significant advantage. It performs sorting in place, requiring only O bracket 1 auxiliary space. This memory efficiency makes heap sort particularly valuable in memory-constrained environments. It provides consistent performance guarantees without the additional space overhead of merge sort. However, unlike merge sort, heap sort is not stable. It doesn't preserve the original order of equal elements. One of heap sort's most practical applications is in priority queue implementations, where the heap structure naturally supports efficient extraction of the highest priority element. Its predictable performance and minimal memory footprint makes it a reliable choice when optimizing for space constraints. Throughout our presentation, we'll examine how these algorithms function in practice, explore our findings from AI chatbot analysis, and demonstrate their real-world applications through our implementation examples. We'll particularly focus on how these algorithms can be applied to solve practical computing problems. My teammates will now continue with a deeper examination of these algorithms, starting with their detailed mechanics and properties.
Thank you, Ruben. I'll start off by giving a quick overview of merge sort itself. Merge sort uses a divide and conquer approach, splitting an array into smaller subarrays until each is trivially sorted. These subarrays are then merged together, resulting in a final sorted array. The process guarantees a consistent O n log n time complexity provided stability at preserving the order of equal elements, especially valuable for multi-level sorting tasks. Comparing the usefulness of these chatbots, starting off with Copilot, the responses include iterative, in-place, block-place, and parallel merge sort variants. Such coverage shows that the merge sort can be adapted for various system constraints and performance goals. From external sorting in database management to ghost spatial processing, Copilot illustrates where merge sort truly shines at scale. However, its drawback is that the broad coverage may limit the depth of explanation for each specific variant, leaving users who need a more focused, detailed discussion wanting more. In comparison, GPT-03 Mini High focus on nuance comparison. This chatbot goes into detail about specialized variants like natural merge sort and hybrid approaches such as stem sort, showcasing how merge sort can be tuned for different data patterns. By highlighting the multi-level sorting, parallel computing, and large-scale data sets, GPT-03 Mini High underscores the algorithm robustness and reliability. However, its drawback is that the detailed explanation assumes a higher level of familiarity with computing concepts, which could be less accessible for the beginners. In summary, although both Copilot and GPT-03 Mini High have some drawbacks, they not only break down the inner workings of merge sort, but also offer practical guidance on how to optimize and apply the algorithm effectively. This clarity and depth serves as a useful resource for both developers and learners alike. Next, I'll pass on my time to Zoe.
Thank you, Chiari. Now I'll be talking about heap sort. So heap sort is a comparison-based algorithm that uses a binary heap tree data structure to sort elements. It works by first transforming the unsorted array into a binary heap, which is a complete binary tree that satisfies the heap property. So the O3 Mini High chatbot provides a detailed step-by-step explanation of these phases. It uses print outputs to show when heapify operations and swaps occur, which makes the process very accessible for new learners. However, one drawback is that its discussion on heap sort's non-adaptive nature is a bit brief, where it doesn't fully explain that the algorithm doesn't take advantage of partially sorted data, unlike adaptive algorithms such as insertion sort. On the other hand, The Sonnet chatbot offers a structured and comprehensive breakdown. It covers not only the mechanics of heap construction and sorting, but also delves into the algorithm's trade-offs such as its lack of stability and poor cache performance. It even compares heap sort with other algorithms like quicksort and merge sort. One shortcoming, however, is that Sonnet states heap sort uses O1 auxiliary space without clarifying that this holds true only for iterative implementations with recursion. The call stack might add an extra big O of log n overhead. For the application part, the basic application of our algorithm involves applying heap sort to an unsorted array of integers into a max heap, which is a complete binary tree where every parent node is greater than or equal to its children. This is achieved by repeatedly performing heapify operations starting from the last non-leaf node up to the root. After constructing the max heap, the algorithm sorts the array in place by repeatedly swapping the root, the largest element, with the last element of the current heap, reducing the heap size and then calling heapify again to restore the heap property. This process places the largest element in their correct positions one by one. In summary, both chatbot responses are insightful in their own right. O3 Mini High's narrative approach makes the algorithm easy to follow, while Sonnet's detailed analysis offers a deeper understanding of heap sort's practical implications. Now I'll pass my time to Joanne.
Thank you, Zu. Now that you know more in depth about the different algorithms we're going to use, let me walk you through the real world application. Moving to the Google Colab, we have a basic model of how we'll be utilizing merge sort and heap sort, where the priority, execution time, and job name will be pushed into the main heap as a tuple and ensures that jobs are stored in priority. During the process job function, the job will be extracted out using heap pop and added into a dictionary called priority groups, with priority as the key and the execution time and job name as the values. This is where the merge sort will come in. Sort out the dictionary in ascending order, and jobs with the same priority will be sorted by execution time using merge sort by splitting the list into two halves and recursively sorting them. Utilizing this concept, a machine learning system was created where there will be a list of tasks that the system needs to perform and run according to priority level. Using the heap sort and merge sort, inference tasks will first be applied where the system will ask the user whether they will be using Google Colab, the data file type, and the name of the file for the system to find, followed by feature engineering where the user can select to use label encoding or hot encoding, as this system is for classification models, data cleaning, and lastly machine learning, where the user has to select the input feature and target labels, select the model they want to use, enter their priority level for testing. The heap sort and merge sort will be used to go through the dictionary, run according to the priority level, and the classification report for each model will be printed out. Now I'll pass the time to Azim to talk about his part.
Thank you, Joanne. Now let's get back to the slides. So, this brings us to our conclusion. Comparing Copilot with GPT-03 Mini High, we see that while Copilot does provide more details, they aren't necessarily useful and can be redundant or repetitive. They also fail to pinpoint certain key details at crucial points, for example, failing to introduce the key aspect of merge sort. On the other hand, GPT-03 Mini High is able to determine the important aspects of merge sort and outline them clearly for the reader. This was further corroborated by the responses for heap sort, providing more accurate information than Sonnet 3.7, thus culminating in a better learning experience. As a whole, however, all three chatbots fail to dive deep into each algorithm's intricacies or their more niche aspects. But we still rate GPT-03 Mini High as the better chatbot out of them, as they provide a more digestible read. And that's it. Thank you.